Let's then move ahead with our quiz. Here's our quiz. Wow, I was writing big, I guess. Let me... And on the things that or activities or tasks that I'm wanting you to do in class, take out a piece of paper, put your name clearly in the upper right-hand corner. If you're ripping it out of one of those spirals, can you try to tear the spirals off before you turn it in? That just helps me. Then I don't get frustrated quite as much. Thank you. Now, you'll have a few minutes to find V sub L of t, this voltage, across these two nodes, given a supplied voltage across these two nodes. Well, I'm looking at the time. Are we done? Take a couple more minutes. Or think about how you can solve that. It's now 12:54. Let me give you 5 minutes to work that, or at least get started on it. Everybody get an answer? Don't see very many confident faces. Did you have a good break? How many, well, I don't think this harms anyone. How many took 220 last semester? How many took it before last semester? Okay, I'm just curious what our mix is in terms of how many have just seen 220 and how many have taken 220 maybe a little bit before last semester. Now, everybody should feel okay with the circuit structurally, and so that's why I've gone ahead and expanded it up to 100%. And now what if you don't really even know where to start? Let's just try to, what I want you to do is start developing strategies or techniques to begin to feel more comfortable or confident with your ability to solve some of these problems. In this case, if you don't even know where to start, how do I want to say this? Let's say that you, guess I shouldn't do it in highlight. I was really trying to emphasize it. But let's say you don't know where to start. One thing that you can try to do is simplify the problem. So that's something you might just try. You might say, well, let me see if I can simplify the problem. Or what are we really saying? You want to get your feet wet. You want to dive in. You want to, if you were in the dirt, you want to get your hands dirty. How do you do that with this particular problem? One thing that I would do looking at this, if I didn't really even know what to start, first off, what's exciting this circuit? What are we applying as the input? A sinusoidal signal. And we may actually have to make an assumption. I was very vague in writing this problem down. You might have to say, wait a minute, is this starting at time t equals 0, or is this happening for all time? Am I in a steady state condition, or am I having to worry about the transient that might happen when I first turn this on and then I create this sinusoid at t equals 0? That's a question you would have to state what you're assuming or not assuming. But in this case, let's say that that particular signal has been on for all time, and that's not that important for getting our feet wet. But in this case, getting our feet wet, maybe what's making me nervous are those squiggly things, those inductors. Just forget them. Just get rid of them. Don't even think about them to begin with. We're not going to get the correct answer, but at least we'll get a feel for what could happen. So let's just throw them away. And how do you throw inductors away? You probably want to short them out, right? You can't just remove them. If you remove them from the circuit, you're going to disconnect everything and you won't get anything at the output. But if we zero those inductors, that means replace them with a wire, a short. That's going to help us maybe simplify this problem. If we do that, we've got two inductors. If we simply throw away or neglect, maybe throwing away is the wrong word. Let's say neglect the inductors. If that's the case, now I have something like this. And maybe, I don't know, is this notation messing you up? Are you more comfortable doing this? Hopefully we'll all be okay with whatever notation I'm using, but this is now V sub s of t. This was the line impedance, or the line resistance, and this was the load. And the way you can tell that is because of the way I said it. It was R sub L and R sub L. R sub lowercase l, R sub uppercase L. This is the line. You don't know this, but you can just say, okay, this is R sub lowercase l. That's the line impedance. This is the load. And we were given particular values for those. Lowercase l was 2, and uppercase was 78. Now do you have, and this is not V sub L, so maybe I should say that's a V sub L hat. It's not the real V sub L. But at least maybe he'll give me partial credit. We're all into partial credit, right? So maybe I'll get some partial credit if I solve a problem. At least I show him what I can do. I can at least do this problem. And that's true. And this will actually start building up your confidence, because what are you now seeing? What's V sub L hat going to look like relative to V sub S? Should just be a fractional piece of V sub S. It's going to look just like V sub S of t in terms of, what do inductors do to frequency? Are they frequency dependent? Do they worry about frequency? And then, I'm sorry, what did I say? Inductor? I meant to say resistor. So I pointed at this and said the wrong thing. It's not that squiggly. This is just straight lines. That's supposed to be a resistor. What's a resistor do to a time-varying waveform? Or is it doesn't depend on frequency, does it? That means that V sub S of t and V sub L hat of t are related, really by a scaling. And if you see the voltage divider, it's the voltage divider. If you don't see that and you want to analyze the circuit, maybe you say, well, how do I always analyze these? I want to find this current I, and if I can find the current I, then I can multiply the I times R sub capital L, and that will give me V sub L hat of t. And that's now some proportion of V sub S, and it's most of V sub S by the relationship between the size of R sub capital L and R sub little l. Not much is dropped across the line in this particular case. Is that making sense? And now, if you didn't do anything else, you at least say, okay, well, I can solve this. Either by the voltage divider or find I of t, and then you can say V sub L hat of t is just R sub L, capital L, I of t. Is that making sense? And now if you had something that's varying sinusoidally, and what was the frequency of that variation? In hertz, in cycles per second, what was V sub S of t? 60. So that's coming out of our wall. Could be. We're not in Europe, which is maybe 50 in places. We're here in the United States, and it's going to be 60 hertz coming out of the wall. And that's in cycles per second, or hertz. We like to work in, whoops, that should not include the t. We like to work with omega, radians per second. And that's now 2 pi times 60. 2 pi is about 6, so it should be around 360. It's actually bigger than that, obviously. Pi, everybody has that memorized to 72 digits. Yes? You should have covered that in 220. Shouldn't be in this class unless you know pi to 72 did know. But pi is 3.14, right? 159, that's plenty. It ends up being omega is 377. So now if we go back, roughly, now that we feel somewhat comfortable with this simplified, what would you expect to happen if we throw some inductors into those two places that we threw them in the original? Pardon? They do depend on frequency. The comment was they will introduce some more impedance. Yes? And that impedance will be frequency dependent, and that's why that omega value is important. That omega value being 377 is important because that inductor's impedance, how it behaves, depends on that frequency of 377, and that was fixed for our source. Now, if we change the source and said, oh, I just want it to be at 10 hertz, then it's going to be a different omega, since it's a different F. And our impedance values of those inductors will differ. But now if we change the impedance, actually what do inductors do? They actually give us more than just a magnitude change of impedance. They change its phase also. So they have a magnitude and a phase, and now we have impedances that are complex. But what have we done to the frequency at V sub L relative to V sub S with this circuit? What have we done with the frequency? Is V sub L of T, and I always go and I say, okay, if we have a system and we kick it, what's it going to shake at? Well, now we're shaking it at 60 hertz. 60 times a second we're shaking it. That's how we're exciting it. What's going to happen at that output? Is it going to shake like this? If we were shaking it like this, it'll be exactly the same, won't it? We won't change the frequency. This is a linear system. V sub L is going to have the same omega of 377. And if we looked at the peaks and valleys with V sub S and V sub L hat, how were those peaks and valleys aligned? In just the pure resistive circuit. They were exactly aligned, weren't they? If I had a peak here for the V sub S, I would have a peak with V sub L. And we just said that V sub L hat was some scaled version. I'm going to do this poorly, but let's say this is V sub S, and then we could say, and I'm going to exaggerate this, but this would be V sub L hat. It would be following or in step, in lockstep, the same frequency. That's a terrible sine wave, but you can do better. You can now sketch that, and those are aligned. Now, what happens when we put that inductor, or those inductors back in place? We get a phase shift, don't we? The period of that wave is going to remain the same. Or the frequency, it hasn't changed. It's just going to shift now. And maybe it will scale a little differently now. But do you see now what you would expect? If somebody came and they said, oh, here's the output, V sub L of T, and here's the input, V sub S of T, do you have a feel for how you could instantly sort of check that result? You would say, okay, are the frequencies the same? Are the periods the same? Are they lined up? If they're lined up, maybe I would say, wait a minute, there's some inductors in there. There's probably some delay, some phase shift. And what would you expect? Probably the amplitude to be less than what it was to begin with for V sub S. That's your gut feel for how this circuit behaves. Is that making sense? And you have that knowledge, you have that insight coming out of 220. That's what I want to convince you of today. You can solve this. You can solve that circuit. What were some of these well, we needed to worry about? So let me just write down some of the things that you hopefully maybe did a little bit further than we did with that simplification. You should remember this even more than between 220 and 320A. You should remember that relationship until you retire. Okay, maybe you're going to retire in 5 years, okay. But if you have a 30-year career, you should still know that relationship. Omega is 2 pi f. Yes, that shouldn't be that hard. And you told me that F was 60. And if you are now in the United States worrying about power problems, dealing with line frequencies, you're talking omega of 377 radians per second. Okay, so that you would know. And why do you need that? Because we need to find the impedance of these inductors. And the frequency is important. Because we are working in, well, you told me, sinusoidal steady state. And because of that, now, what did you learn in 220? Let's not continue to play with sines and cosines. Let's realize we've got sines and cosines and just play with complex numbers. That's a lot easier. Then we can play with algebra. And we're going to even make that more general. We will not just have our impedance being j omega L for inductors. We'll have it equal to lowercase s, as in Sam, L, SL. That's the Laplace impedance of an inductor, where S is not just j omega, but it could be sigma plus j omega. So now our S can be a complex number. That's what we will learn in this class. We'll start generalizing things, but what are we doing? We're generalizing and using tools that help us simplify the analysis or make the analysis a little more easy to perform. Rather than working with sines and cosines, you learned how to do phasors in 220. We're now going to generalize this notion of phasors in here to be the complex frequency variable S, which is the Laplace variable. Now, if we're dealing with phasors, I just said that the impedance of an inductor is j omega L. And for the load inductor, I subscripted that with the capital L. I think I gave you a value for that. What was it? 156.5 millihenry, or 0.156. So it's 15% of 380. Or if we do this, did somebody get 59 for the impedance of the load inductor? Good, we got one more point out of 100 on that problem. Partial credit, right? So there's Z sub capital L. While we're doing it, we might as well do, since we're getting the right answer, let's keep getting right answers. Here's Z sub lowercase l. This should look the same, except now it was some smaller value. It was 2.653 times 10 to the minus 3. And this, did you end up with J1? Those are now our impedance values for the inductors, and those are complex, or those are purely imaginary. And I'm going to try to be careful with the way I talk in here. When I say a complex number, that usually means it could have a real part and an imaginary part. If I say an imaginary, it may just be the imaginary piece. And if I say we have a real number, you don't have any of these imaginary components. Okay? And what does this look like? The impedance of our resistor. You told me it was not depending on frequency, and so that's now, if that's the right number, that's just R sub L, lowercase l, and Z sub R sub capital L is R sub capital L, and was that 78? So those are some of the, and if we're solving this using phasor notation, don't get dizzy if I'm doing this. Sometimes you may want to take Dramamine before class if I start going up and down on the screen. Hopefully I won't make anyone sick doing that. But how do we change this time domain waveform into a phasor? You have to worry about the magnitude or the amplitude of the waveform, and then you worry about the argument, right? And since there is none so there's no angle after the t, we have omega t plus, well, we do have an angle. We have omega t plus 0 degrees. This now is a phasor of an amplitude, a maximum amplitude, and we'll have to distinguish between maximum values and RMS values, especially when we're dealing with power. Because power, sometimes it's easier to just keep track of RMS numbers. But the computation, the calculation is exactly the same. Once you start with RMS units, you can just carry all the computations through. But you need to make sure, is this a maximum value or an RMS value when you're analyzing the problem? Because that will make a difference in your numbers that you use and obviously then in the calculation. But if we now wanted to convert v sub s of t, which was that in the time domain, and maybe, well, we would have had to assume whether that was turning on right at t. Boy, my handwriting is getting worse, isn't it? But you know what I'm trying to say. This now would give you and I may get sloppy with this, but the phasor, I can't bold it here, so I may put a bar over it. That means it's a phasor quantity. Capital V sub s is going to be, and it has units of volts. We haven't changed that in any way. Where this, you might need to write it down or keep track of, this was the maximum value of that waveform. So this was you could have done the RMS, and you might either denote it that way or you might just keep track of it on your paper. You might say all of my numbers are RMS units. If I now said what's the phasor for the input or the source in RMS numbers, what would you say? Now we have it divided by the square root of 2, and we haven't changed the angle at all. So this is now, if we divide 311, boy, we just want to keep getting more students in here. The numbers are going to be high. Oh, I'm sorry. I shouldn't mention that. I just had the door open and you were oblivious. I should have just left it that way, right? So this is now, if we divide 311 by the square root of 2, this ends up being 220, and that's actually a numerical value that you might see in a power system here in your house. For example, your dryer might be supplied with 220 volts, and then it doesn't require as much current, etc. Maybe it's more efficient. So that's now the RMS, and we've done a voltage divider, or we could solve that. Now if we were interested in the power, what would we want to know? I didn't ask this, so we're sort of done. If we analyze this, we could now use this input or the other one, max or RMS. We have our impedances. Maybe I should write that down. So to complete this problem, we could now say that we have some circuit. This was 2, this was J1, this was 78, and this was J59, if my memory is right. And this was, let's just say that it's 220 at 0 degrees. And that was in RMS units. With that, we can now use complex expressions for our impedances. We could solve for this current. Once we found I sub t, we could multiply that by our load impedance, 50 or 78 plus J59, and obtain V sub L bar. V sub L bar will be a complex number. It will be a phasor, and we can now put that back into the time domain if we want and sketch that relative to V sub S of t. Is that clear? Now that we have V sub L of t, how do we find the power absorbed by that load? Or is the power delivered by the load? How do we know? That's what we'll start learning in this class immediately, actually. What would you expect? What does this represent, maybe? What might that represent? Some motor. The motor might have some resistance and some impedance. There we have a motor. And this might be the power lines, the transmission lines that are going to that motor, and now we're driving that motor. We might be interested in the power consumed or being consumed, or how much power are we delivering to that load. That's a question that we'll start answering in this class. And if I'm interested in power, what do you know about power and voltage? Or power and voltage and current? Do you remember what power is? Do you remember VI? Voltage times current. That will give you, if those are time domain voltage and current, you'll now have instantaneous power. Meaning, if you have now found I sub capital T bar, you now have little I of capital T in the time domain if you want to. You can take it into the time domain. You can now take this guy, the load voltage, into the time domain. You can multiply those two together, and now you have the instantaneous power waveform associated with that load. Maybe we don't want to know what that's doing at 60 times a second. We want to know what's the average power, and that's what we'll start talking about. We now, though, know something a little bit about power. P of t is V of t, I of t. That's this instantaneous power. Maybe somebody says, well, I don't care how, it's shaking a lot. I just want to know what's the average power. If you have a hair dryer, how do you designate that hair dryer? If you go to the store and you go, I want a hair dryer, what might they ask you as a question? How many watts? Or if you have a microwave, if you're cooking food, what do they say on the package? They always say, this may depend on the power of your microwave, right? They're using electrical engineering. Depends on if you have an 800 watt or 1,000 watt or 1,200 watt microwave, how fast or how long you need to shock it or cook something. Yes? Same with your hair dryer. What's a nominal hair dryer? Zero. Nobody dries their hair anymore. Oh, that's fine. Good. We're green. We're greener now. But typically it might be 1,000 watts, 1 kilowatt. That's roughly 1,000 cell phones. Cell phone's about 1 watt. So a hair dryer is consuming a lot. And if you ran it for an hour, you dried your hair for an hour, that's a kilowatt hour. That's some amount of energy that you've consumed, and the power company will charge you for that. And maybe they'll charge you a dime for that. So that cost you a dime to dry your hair for an hour. Wouldn't cost you that much to charge your cell phone, would it? For an hour, relative to a hair dryer. Is that making sense? If your cell phone is maybe powered, if you're communicating, maybe it's now, or if you're talking, maybe it's consuming 1 watt. And you guys are going to have to go out and design things that operate at very, very low power levels. Why? To try to be as efficient as possible. So it's important to understand what you're doing with respect to power, or how your system is behaving relative to power. In this simple circuit, if you were wanting to be as efficient as possible, what would you want in that line diagram? You would want that line, the little lowercase l, to be 0. You would like to not lose any power from your source to your load. You would like to deliver as much power as you can to your customer if you're the one doing the supplying. And what do you think the power company is going to do? They're probably going to charge you for that loss. So we want to try to make sure that we understand what's going on, how much power we're getting at the load, how much is happening at the line. So we might be talking then about average power. If we know the instantaneous power, how would you find the average? All right, we have 50 students. What's the average weight? Okay, so we just average over the length of the period, don't we? We integrate, or we sum all of that waveform over a period or multiple periods, but we would have to divide by those multiple periods. In this class, if there were 50 of us, we would add up all the weights and divide by 50. That's what we're doing to find the average power here. We would have this instantaneous waveform. We would find one period of that. If it's steady state, it looks the same at this period as it does at this period as it does at this period. Let's just look at the average. We integrate over one period and divide by that period. Now we have the average power. Is that making sense? What happens though now is you're sophomores, juniors, somewhere in your electrical engineering curriculum, you're probably going to have to do more than just compute the average, right, to get paid the big bucks. So we have to know something more than just, oh, find the average. Somebody could maybe do that with Excel. You need to know more than that. And what we will now start learning about is how do we keep track of reactive power. And what is reactive power? Well, we'll look at what these inductors look like and what these capacitors look like. They're now building up energy in a magnetic field and then giving it back. Building it up, throwing it back. The capacitor, it's energy in its electric field, and then it collapses and gives it back. And it's now throwing we now have voltage and current going back and forth between the source and the load because of these reactive components. The company's going to be concerned about that. And they're going to be interested in the reactive piece, and so are you as, let's say, the customer. Well, if we have the average power and reactive power, we could combine those, and we will, and we'll introduce a complex power, which is a complex sum of the average and reactive. And each of these will start giving different units so that we can keep them straight. What was your hairdryer units? Watts or kilowatts? When we compute power, just remember it's voltage times current. What are the units on that? Volts, amps. Volts, amps. Well, let's just use that for complex. So this will be volt amperes. Complex power. So now I say, oh, you have a load that has 2,000 kVA, kilovolt amperes. Now you know it's something that's complex, possibly. Well, reactive power is not watts, It's not VA. Everything is VA, actually, but we just designate it differently. This we now say is volt amperes reactive, VARs. Oh, you have a load that is consuming 500 watts and 16 VARs. Now you know the complex power that your load is representing. 500 plus J16. See how much you're learning on the first day of class? Then we also have apparent power. I'm assuming that these pieces are somewhat new to you. Have you heard of reactive power? Some of you maybe. Complex power, apparent power. We'll learn a little bit more about those. Now I'm basically going into the overview of this class, just based on that simple circuit. This is now the first chapter. This is chapter, whatever we're starting, 10, chapter 10. This is chapter 10. Then we will that was a single phase system, meaning we just had one waveform or phase to worry about. Now we will start in chapter 11 dealing with 3 different phases that are shifted in time. We'll have an A phase, a B phase, and a C phase. And how we see A, B, and C will determine whether we have a positive phase sequence or a negative phase sequence. See how many permutations I can make on this? It can get very interesting, but you'll figure that all out. We'll examine 3-phase systems. I've already hinted at what we're going to do next. Once we have understood this sinusoidal steady state fairly well and talked about the power in the single phase and 3-phase, then we'll say, let's generalize this. We're not always going to be operating in the sinusoidal steady state. What if we turn things off and on? We might have some transients. How do we account for those transients? How do we model those? Now we want to generalize that's my sinusoidal steady state. And that will be now Laplace transforms. Once we have Laplace transforms, this will allow us to the opportunity to follow these transients through our waveform and circuits, and we'll start to learn how long transients might or might not last. And is it a second? Is it 10 minutes? What are these transients and what are their duration? And we'll get more comfortable with that. We also obviously would like to continue to worry about the steady state behavior, or what our system is forcing us to work with. That was the source. F sub or V sub S was forcing us to be working at 377. That was our forced response. And if we shake something, a linear system at that frequency, everything in that system is going to be shaking at that same frequency. There may be some transients, and how long those last will depend on how fast they decay. And we'll start learning a little bit more about that. And Laplace transforms allow us to incorporate initial conditions. It will also, boy, these Laplace transforms are good things. And have you guys all had Math 322? Are you taking Math 322? Or some of you may not have to take it, depending on your catalog year. Well, in 220, how big of a circuit did you analyze? How many R's, L's, and C's did you typically keep track of? How many inductors and capacitors in one circuit did you have to analyze? Usually it was either an RL or an RC, first order circuit, or it was an RLC circuit. You could combine them into just being an equivalent capacitor and an equivalent inductor. So you now have a second order circuit. With what we're learning, we can do whatever degree, whatever order you want. Give me 5 inductors, 16 capacitors, have at it. We'll be able to do it. We are going to then be able to work with higher order circuits. We're not going to be limited to just 1 or 2 energy storage elements. And by energy storage elements, I'm meaning capacitor or an inductor. Capacitor, it stores energy in the electric field, the inductor in the magnetic field. These are now L's and C's. Now that we have this machinery, now that we have a circuit, somebody gives us a circuit, we now know how to formulate it in terms of Laplace transforms and analyze it in Laplace transforms. Now we've opened up a new realm. Now we can play with transfer functions that are frequency dependent, that are a function of these complex variables S, or this complex variable S. So now we have this transfer function. And once we have transfer functions, we can do all sorts of fun things. You could now find, if that was a transfer function of a circuit, which tells us how our circuit behaves from the input to the output, we could inverse Laplace transform that transfer function to obtain the impulse response of that circuit. Now you know if you went up, and this would be a mechanical system, have you heard of an impulse hammer? Oh, no, it didn't hurt. But you have an impulse hammer. Mechanically, you hit it with an impulse and it shakes. In a circuit, you hit it with an impulse, and what are you doing with that impulse? You're really instantaneously energizing these energy storage elements, and then you're watching them collapse. That's the impulse response. And if we have 20 different circuit elements, it might be a fairly interesting impulse response. That's what we have. We can also do what we started to talk about earlier. Now that we have these transfer functions, you'll learn how to sketch Bode plots for those transfer functions. And what were Bode plots? What did I tell you to remember when I said Bode plot? What are you seeing now? A graphic equalizer on your stereo, right? Something that's shaped with respect to frequency. It could be a low pass, high pass, band reject. It could be some weird shape, and that's why we need to sketch the Bode plot. Here is our frequency response of some system. And what else? Now that we have the impulse response, if somebody gives us a general input, we can figure out what the output's going to be. We can convolve the impulse response with this generic input waveform. It doesn't have to be a sine wave. It doesn't have to be a step, an impulse, a ramp. It can be anything. We can convolve that with the impulse response, and now we know what the output is. So this is now our opportunity to take these general input waveforms and produce an output response using the convolution integral. And that's all available. We now may want to take these concepts. If we had a transfer function, maybe somebody says, well, I don't know what the circuit is, but I know this is what I want its transfer function to be. Now what are we doing? Now we're designing. And the simplest thing to design first are filters. Let's design some filters. Meaning we're starting with a transfer function. Now let's end up with a circuit. We're going just the opposite of how we've begun this semester. Now we have filters, and those could be passive. Think R's, L's, and C's. Or they could be active, meaning you may have to plug them in or energize those in order to make them work. We will also talk about two-port networks when we're talking about frequency response and Bode plots and behavior inputs and outputs. Now we have an input port, an output port. Now we can generalize that to two ports. This might be helpful in other classes where you might be dealing with electronics or you might be interested in electromagnetics. They use two ports, and so this class hopefully will get to see some of that from a circuits perspective. And finally, because we're running out of time, we can deal with general periodic waveforms. Because once we know we have a periodic waveform, we know that that waveform has a Fourier series. And that Fourier series is made up of a bunch of frequencies, and we know how the system responds to different frequencies because we know the graphic equalizer. We know its frequency response. Now we know how to find its output. We'll have to pick up at that point, but we'll start talking about power, which is Chapter 10. Start reading on Chapter 10, and I'll see you on Tuesday. Have a good, safe, long weekend. Pardon? Am I going to? Oh, yes. Don't let me forget. So when you have an in-class assignment, put it somewhere so that I don't forget it and you get credit for it. Thank you. So do hand in your class participation and make sure I get those attachments that were being signed as you took down notes for today's lecture.